welcome to the video. Today we are going to solve k distance from root. In this question we are given a binary tree of n nodes along with an integer k, okay, along with an integer k. And we have to return all the nodes which are at a distance of k from the root. So look at example 1. You have k which is 0 and a binary tree with three nodes 1, 3 and 2. So nodes which are at distance 0 from root is the root itself for this case. In that case, we have written only the root element because root itself is at distance 0 from itself. But example 2 will give you a better picture to you. Example 1 gave you a base case. Here there are 5 nodes and k is equals to 3. And here it is kind of a skewed tree, not exactly skewed tree, but I mean somewhat skewed. Okay. So here we will see all the nodes which are at distance 3. K is equals to 3, distance 3 from the root. Root is 1. So here are two nodes from 1. Go to 2, 1 and 3. 3 is a distance of 3. You will return that. Along with that, 2, 1 and 5. 5 is also at a distance of 3 from the root, which is k. Since 5 and k were at the same level, so they both came at the answer. So if you remember closely, I mentioned 5 and 3 are at same level. So this should ring a bell that we will be using level order traversal for this. First of all, let me indent this thing. This may give you an error. It gave to me when I solved it earlier. So I create an empty list called result. Okay, and then a base condition. If not return, if not root, if root is not there or we are at the leaf node, then we will return nothing. And then another base case, which was the case in example 1. If k is 0, distance is 0, then we'll return the root itself. We'll return root dot data. Now I will imply level or traversal. So first I'll create number of steps, a number of level, you can call it level also, and a utility function which takes two arguments: root itself along with the step, how many steps it has to traverse. So again, base condition, if not root, return. If there's no root, return, or we are at the leaf node, we'll return it. Now, again, if we have reached at the target position, target steps, if we have reached at the target level, we will return at the end, but we will append this data, this root dot data, current root dot data to the current data to the result, because there can be more than one answer as we saw in example 2. Since 5 and 3 were the same level, so they both were candidate for answers, right? Now this was the case when we have reached this step, but what if we have not reached and we have to further traverse in left side or right side? So if left exists, left subtree exists, move towards it. Again, recursively call our utility function with root dot left this time, and step should increase by 1. Step should increase by 1. Level increase by 1 because we are going deeper. So its number of levels are increasing. Again, if right subtree exists, call the utility function recursively again towards the right side along with one step ahead at a time. One step ahead at a time. Cool. Now that we have recursively called our utility function to go to all the levels till the very end leaf node, we have, if we reached at the step, we appended the result. Okay. Now what? We will call our function with parameters which will be 0, 0 at this step level, and root to begin with, and step initially will be 0. As we go deeper from root towards the leaf, a step or level will increase by one at a time. At the end, we'll return the result which we have populated by moving down, traversing down. Okay, return outside function in 22. Okay. Sorry, this is indentation issue. Okay, since they have destroyed that indentation thing. So as you can see, it does the job pretty effortlessly. It took very less time, despite being a recursive function. So I hope you enjoyed the video and learned a new concept, a very beautiful concept. Thank you. Have a very nice day.